Hello students and friends. In today's video, we are going to see some simulations related to spring mass system. I have come to PhET simulation lab and selected physics. And let's see the masses and spring basics. So here we have different springs, two springs we have, and we have different masses. And we will have this scale if we want to measure the extension of this. We can have here unstaged length, restoring position, and movable line, but we don't want movable line now. Suppose I attach this mass, I just stretched the spring using this weight. You have to just drag the weight and just place here in below the spring. You will see there is an extension in the spring, and now you can measure the distances. This is in centimeters, and from that you can use F equal to kx, and you can find out the spring constant of that spring. And when you do that, what you can do is you can remove the weight and you can attach unknown weight, and using the k you previously calculated, you can find out the unknown mass. So this is the use of the spring. Now here you can see you can change the k value, that is the spring constant. You can change from here and you can see how the effect is there. So for the same mass, if I decrease the spring constant, you can see the extension is more for the same force or same mass. Okay, if I increase this spring constant, the extension is smaller. Now let's go to the next part of this simulation. This is bounce. So here what happens is if I attach here, it will oscillate. So here you have extra timer and there is a scale also. You can also use this. Now here what we can have, let me pause this. You can have here pause button. Here similar to the previous, we have unstaged length, we have resting position. This means if there is no oscillation, where the mass will rest, that is called as a resting position. So for example, if I attach this 100 gram here, so this is a resting position. This means now this spring mass system is oscillating with reference to this origin. Okay, suppose I remove this and again attach. Now you can see here, now at this point both springs have the same spring constant, but because the larger mass is attached to the first spring, it is oscillating with more amplitude, and this spring is attached with a lesser mass, so this has less amplitude of the oscillation. Now if we can stop this, you can see this displacement is more if the mass attached is more, and this is obvious, we can see. There is a third part lab where you can attach the mass here, but instead of different masses, here you have a tab where you can change the mass. Okay, now if you see the resting position and unstretched length, if I decrease the mass, you can see the displacement is less or the amplitude is less. If I increase the mass, the displacement is more or amplitude is also more. You can also check what is the timing required for each oscillation. you can see if we have different type of gravity. Suppose we perform this experiment on moon. I'll stop here and again I will try to start. You can see very small oscillation is there because there is no gravity. Now I will stop this. I will change the mass and you can see the oscillation. Now suppose I will stop this and now I will come back to earth. Now you can see this is more. So you can see from this you can check what is the acceleration due to gravity. Now if we measure the time period, so for example we will measure the time period for 10 oscillations. Start. 2, 3, 4, 5, 6, 7, 8, 9, 10. Now you can see almost it takes 8 minutes to complete 10 oscillations. Okay, I will reset the timer and I will go to Jupiter. Let me first stop this and now attach this. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can see for same number of oscillation we are getting another time period. So you can see how it is related to the gravity. Because T is inversely proportional to under root of G, as the G is increasing, T will decrease. So this is the first simulation. Now we will see another simulation which is Hooke's law. We have seen this one, masses and springs, and there is one more on masses of and spring, but I guess both are same. There is not much difference in between these two. Okay, let's quickly check that. Yeah, this part is same, but what they have done, they have added this. This is oscillating and there is also option for gravity. So what happens if gravity is increased? So you can simultaneously see. Now you can see here there is interesting thing. The spring length is different for both cases, but the spring constant is constant. So let me add this 100-gram weight to both the springs and let's see. You can see because the spring constant is same, the extension is also same. You can check with this scale. Okay, here is this expansion 0, this is 15 and here is also 15. So you can see the spring constant or the extension does not depend on the length of the spring. Now suppose if the thickness is same, now because thickness is same, the spring constant is different for different springs. Okay, so you can see as the thickness is increasing, K value is going to increase, and therefore you can see there is a difference in displacement because length is same, thickness is same, sorry, not length is same, thickness is same, but length is different, therefore K value is also different. Now there is some vectors. Okay, okay, here what we can see is, oh, what happened? Yeah, so you can see here the displacement. Okay, and if we see velocity, so it is showing the direction. So acceleration also we can see. Now you can see The direction of velocity and acceleration are always opposite to each other. Now you can see the direction of gravity is always same, so we will not see that. Now the direction of force, you can see it is always bringing upward because the force of gravity is always downwards. You can see here. And if we see the net force, so this net force is also oscillating with this spring, therefore it is oscillating. So you can see it is kind of forced oscillation, but it is happening naturally. Now here we have option to slow down this. Okay, let me try one thing. Suppose I start this. Okay, this timer is also slowed down, so this is very good. We can measure this accurately. Okay, let me stop this, reset this, and bring it this to normal. Now this is also becoming normal, so you can see. Now let me click slow. Yes, you can see both are becoming slow, so you can see very accurately what is happening here, and at the same time you can measure a time also accurately. So this one is very good. Now here we have energy part. What happens when I apply this energy? You can see here what happens to kinetic energy, potential energy, and potential energy of the spring. If there is some thermal energy, that is also shown here. So suppose I increase the mass, then you can see the energies are going to increase. Again you can see the displacement and mass equilibrium. If this is increased, the potential energy is half kx square. So if x is increased, this potential energy is also going to increase. And how this x is going to increase? If we attach more mass. So suppose I decrease this mass, you can see the energy is going down. Now what happens if I increase the k? Again k is directly proportional, or energy is directly proportional to k, because kx square. So if you increase the k value, you can see very slight change in the k value, because force is not changed, and as k is increased, x is decreased. Yes, you can see here. You can see for smaller k value, displacement is more. For larger k values, this displacement is less, and therefore, and it is proportional to x square. Energy is proportional to x square, and therefore, because even if the spring constant is increased, the potential energy is not much increased, because x is decreasing. But if mass is increasing, now you can say displacement is increasing, and it is proportional to x square, so it is increasing with large amount. So suppose I take one value, and here you can see damping. Okay, okay, let me have largest mass possible here. This 300 gram, and we are measuring the height from here. Okay, this is ground, and now I will attach this mass here, and if I increase the damping, so damping is something which is opposing this motion of oscillation. Earlier we don't have this option of damping, so here you can see if damping is more, this spring will rest quickly. Suppose I add a maximum damping, so let's say this is in some medium. See, it is stopped within 2 or 3 cycles. Now I will decrease the damping, and again if you see, now it is oscillating, but the amplitude is going to decrease gradually, and after some time the oscillation will stop, and this will attain its equilibrium state, right? You can see the amplitude is going to decrease, and now in few seconds it will become at equilibrium state. Now again, if we go to this labs, again you can see here velocity, acceleration, and all this. Here we have period trace. Last time we haven't seen this, so let's check this. So you can see it is easier to measure this, and now you can see this amplitude is going to decrease. You can see this very clearly. Let me increase the mass. Yes, after increasing you can see this, and let me increase some damping. So you can see how quickly the amplitude is going to damp, right? Here also you can see the direction of velocity and acceleration. Because they are almost zero, let me add this again. Now you can see, you can again slow this down and observe, and after slowing down you can measure the period of the spring. I will make this normal, and you can change the gravity here, you can change the damping here, right? Okay, so let me check one more simulation is there. Hooke's law, yes. Now here what we have, from this diagram we can see the spring is not vertical, it is horizontal. Okay, so let's check. Now this introduction, we just have this variable spring constant and applied force. Currently there is no force applied on this spring. Okay, suppose I increase the spring constant, there is no change, you can see, because it is at natural length is not going to change, but you can see the thickness is varying. Okay, so at lowest spring constant the diameter of that wire is lower, and as I am going to increase this, thickness is going to increase. Okay, so I will keep at 500, and now I will start applying the force. You can see here, and you can here look at the applied force, spring force, and displacement. Now because this is not oscillating, the spring force, that is recoil force, and applied force are equal and opposite, and you can see the equilibrium position, and you can also see the values. Okay, so you don't have to calculate anything. You can see K, you can see the force applied, so F is equal to Kx, so you can calculate this from here. Now if we have another spring, so what we can do here, we can check or we can compare these things. So again, okay, I will keep this spring constant, and I will add here the force. Now you can see, because the spring constant is less, for the same applied force we have larger displacement. Okay, it is also obvious that if this diameter or thickness of the spring is increased, the spring constant is going to increase. This means higher spring constant means there is a less deformation in the spring if the same force is applied. So you can check from this. You can also keep the spring constant and vary the applied force and see how the difference is there. What is the difference in between these systems? Now here what we have two springs attached parallel to each other, and now we are going to apply the force. Now currently there is no force, and therefore displacement is 0, equilibrium position and displacement is also same, original position is same, and we can see the values, but we will see that later. Now suppose I apply some force. Okay, let's say 75 Newton. Now let's see the value. Now because of this 200 plus 2, okay, let me increase this. Let me increase this. Okay, okay, let's keep this. So now both springs have different spring constants, but the total force applied on this is same, that is 75 Newton. And because this is in equilibrium, we can see this kind of extension is there. Now K1 and K2 we can say, so one is 400, another is 200. So if we increase this to 300 and this also to 300, you can see the same displacement is there. So this means if the springs are attached parallelly, no matter what is their independent k values are, but it is important to see what is their combined k value. Okay, so this is for parallel system. Now if we see, if we go for series, we will see there is some difference. Okay, let me go for 400 first, and I will try to keep the same force 75. Yeah, now you can see there is a displacement. If the right spring is 400 Newton per meter and left spring has K equal to 200 per Newton per meter. Now again I have kept the same values as I used earlier for the parallel springs. Now you can see there is a different value of displacement. This means there is a different formula for combination. So let me check. If I keep this both 300, can I get the same value? No, I didn't get the same value. So this means there is addition by reciprocating the k values. So 1 upon k is equal to 1 upon k1 plus 1 upon k2. So from that formula you have to find out the resultant k value or final k value. Okay, so from that you can calculate this. And let me try one more thing. Let me keep this 200 and then 400. Now you can see again I got the same value when this was 400 and this was 200. So flipping the springs will not make any difference. Okay, now again here we have energy. So if I increase the spring constant and displacement, you can see as I am changing the displacement here, the potential energy is going to change. Now if we have energy plot, so as I am going to change this, you can see there is an oscillation and displacement is varying, and with that displacement how the potential energy is going to change. Now we can have force plot and energy plot. So because you can see force is directly proportional to the, or displacement is directly proportional to the force, it is a linear line. And here for energy it is not linear, it is a quadratic curve, because E is proportional to x square. Okay, now you can also see the applied force and displacement direction, what is equilibrium position, and okay, values also you can check. Now because it is not oscillating, it is stable, you can see at that particular instant what is the value. When x is this, what is value of potential energy, you can all check from here. So these are all related to spring mass system in the PhET simulation. In the next video we will come up with another interesting simulation. Thank you for watching. Like, share and subscribe. Thank you.